now.
All right. Thank you very much, Patrick, for the invitation, and everyone else for joining me here. Today, I'll be talking about partition into prime with the Chebotarev condition. I'm going to focus on this Chebotarev condition really towards the end, because whatever I say about the primes in arithmetic progression will more or less be true for the primes with the Chebotarev condition. So just for the simplicity, I'll focus on primes in arithmetic progression and give just an overview of the statement of the result, how it changes for Chebotarev, primes with Chebotarev condition. All right, so to start with, what is an integer partition? You want to write n as sum of positive or non-negative integers, and you don't care about the order, so you count them as one. So you put this restriction that lambda1 is larger than equal to lambda2 and so on, and because you don't want to count zeros, so this is only for positive integers. You can visually realize this through Young diagrams. So for example, 10 can be partitioned as 5, 4, and 1. So you either write it as 5, 4, 1, or you can actually write these 5 boxes in the first row, then 4 boxes below that, and 1 box below that. So this is called a Young diagram. Now, if you want to say that, oh, I only care about my partitions where the parts lambda j's come from a given set A. So you take A to be a subset of natural numbers, and you put this extra condition that all the lambda j's are from the set A. For example, and throughout this talk, we will denote by P sub A n to be the number of ways you can write n as sum of these lambda j. And lambda j's are now from this set A. So for example, if you take the number 5, you can partition into positive integers in 7 ways, including 5, then or 4, 1, and so on. However, if you restrict to the fact that your parts are only odd, then you realize that, okay, you only have 3 of them, because 4 and 2 are not odd numbers. So each of these 4 partitions over here disappear. You don't count them. So now the question is, what happens when your partition, the number that you want to partition n, it becomes really large? How does it grow? So if you have seen the movie The Man Who Knew Infinity, you might remember that there they discussed the number of partitions of 50 and the number of partitions of 200. For 200, it's already in 13 digits. So this function grows exponentially. And this was for the first time proved by Hardy and Ramanujan in 1918. And they showed that this function is asymptotic to this quantity here. Throughout this talk, f asymptotic to g will mean that the ratio goes to 1 in the limit. So in this case, as n goes to infinity, this over this will go to 1. And this is when they originated the circle method. It has been modified to give many other asymptotics, and you could use this to not just for partition asymptotics, but for some other, for example, varying problem and so on. The other ways to show this, that this asymptotic is true, is Stovarian Theorem. And in 1942, Erdős gave an elementary proof, which was basically just avoiding a lot of complicated machinery involving complex analysis, major arc, minor arc, and so on. But for Stovarian theorem, you end up using the monotonicity of the function in advance. So however, if you use circle method, you could actually prove the monotonicity just by seeing just by how the proof goes. Bateman and Erdős actually proved this monotonicity for any partition, any set A, and the number of partitions from that set A, as long as your set satisfies certain conditions. And one of them was that each of the GCD of your set A is 1. So in the sense that all elements of your set A have greatest common divisor to be equal to 1. Erdős compared partitions when your parts are coming from two different sets. And one example of this goes back to Euler, who showed that the number of distinct partition into distinct parts and the number of partitions into odd parts is exactly the same. So now you want to understand, okay, for what all sets A and B can you get some asymptotics and some function which could depend on A and B, of course, but could you say something like this for some general sets? So these are the problems or the ways of handling asymptotics. However, there are some other problems like parity problem. By parity, what I mean is you count the number of n up to m such that your set P sub n, or you could replace n by any a, this is even. So the number of partitions is even, or of course odd respectively. And now you want to understand this numbering as m goes to infinity. For example, if m goes to infinity, are there infinitely many such partitions? So in the sense that are there infinitely many n's for which Pn is even or Pn is odd? Well, if you are talking about just this P sub n, where your set A is equal to the set of natural numbers, it is expected that if you divide this by m, this in limit should be equal to 1. Sorry, 1/2 as m goes to infinity. And same is true for odd. So this is the parity conjecture. However, the state of reality is still very far from truth. And so this number should be, for example, okay, so this should be about m over 2, right? But the lower bounds for this are only up of the order square root of n, or some log, up to some log factor. So we expect this to be, sorry, this should be m. So we expected this to be full power of m, but we only have about square root of m. So this is pretty far. And like this is only for this setting. If you change your set A, then the only result that I know is here this was the result of mine with Bent and Zaharescu, where we showed that this is true for when this, so let me call this A here. And so when A is the set of powers, so let's say m to the power k, these are the kth powers. So we don't even, and our result only says that there are infinitely many n's for which this is even and infinitely n's for which it's odd. So we do not even have any lower bound. So just coming up with any lower bound itself is, of course, not trivial. And it would be very interesting if one could get something like this for other sets A. The other question is about congruences. So Ramanujan's favorite congruences or famous congruences here. Sorry, my pencil has. So, oops. Okay, it just deleted everything. It was too slow. I'm sorry. Okay, so let's just write down the congruences. So Ramanujan wrote this congruence. I will just write one of them, that if you partition a number of the form 5n plus 4, then the number of such partitions is a multiple of 5. Similarly, there are mod 7 and mod 11 congruences, but you could also study this now again, n replaced by a, and if you have a different a, what congruences could you get? That's another question. But for this talk, we are only going to focus on the asymptotics for a particular type of set, including involving prime. All right. So going back to Hardy and Ramanujan's asymptotics that I just wrote on the previous page, we know that it's exponential, but the point is that what is the argument of the exponential function? And so the asymptotics for the log of this partition function is asymptotic to some constant time. We know the constant, it's in terms of zeta. You can see it over here, right? It's 2 square root of zeta 2. But for now, if you just focus on what function of n you have over here, you see that this is square root of n, right? Well, for the time being, also forget about the square root. Just see what's inside it. And it's just n. Well, we are partitioning into n elements coming from this set of positive integers n. So how many elements are there from your set where your parts are coming from? Up to x. Well, there are about x, right? So that's more or less saying is how many parts are there up to n, and you get this n. Okay. Now, in about 20 years after Hardy and Ramanujan gave this formula, Wright gave the formula for number of partitions into kth powers. So m to the power k here. And he showed that, okay, log of p sub an in this case is asymptotic to n to the power 1 over k plus 1. For now, for the time being, do not write it as 1 over k plus 1, but write it as n to the power 1 over k to the power k over k plus 1. Okay, so this is just a different way of looking at it. But you very quickly see that, okay, last time I said that here, don't care about the square root. For now, don't care about the k over k plus 1 power. And if you see that, then you very quickly notice that this is n to the power 1 over k, but that's same as the number of parts that you have in your set up to x, right? So up to x, how many kth powers are there? X to the power 1 over k. So this is very closely related to that. And now going back to the square root over here and k over k plus 1, the general formula over here is k over k plus 1. In this case, k was equal to 1, so it was 1/2, and that's why a square root. And in this case, you end up getting k over k plus 1. So that's the more general part. So you can think of the square root separately and what's inside, or in this case, k over k plus 1 separately, and then the function over here in terms of the set A that you have. So this is quite closely related. So now you are interested in saying, okay, if I change my set A, then how does this A appear in my asymptotic formula, right? So we see this appearance in these two examples clearly, but let's see if it's actually true. Well, primes into partitions were studied earlier, but recently Vaughan studied them in a slightly different way and gave a simpler formula than that was known earlier. And Gaffney, his student, did it for kth powers of prime. So for simplicity, I have written this formula only for primes. So if you want to partition with parts as prime numbers, then you end up getting this constant, which will now depend on the set P, which we don't really care about right now. And again, you have the square root because we are only taking the first power of the prime. And inside you have n over log n. Well, now we want to know how many primes are there up to x. Is that related to this number or this quantity here under the square root? And prime number theorem quickly tells us that indeed that's the case, because the number of primes up to x is asymptotic to x over log. So you see this n over log n appearance. However, we have a better formula for the prime number for the number of primes up to x in terms of the logarithmic integral. I'll define this integral on the next slide, but this is called logarithmic integral. And the first term of this, if you want to find asymptotics for this integral, is x over log. So we see that they actually obtain this asymptotic only as like the first primary term or primary asymptotic term for this logarithmic integral. Now the question is, could you improve it? Could you, instead of just x over log x, could you get logarithmic integral x instead? Sure, it's slightly more complicated and it's not as nice as x over log x, but will that give us a better error term, better asymptotic? So the goal here is to study the generalized version, in the sense that now we will partition into primes which are congruent to a mod q. So this is these primes in fixed residue. And prime number theorem for arithmetic progression tells us that about 1 over pq times the total number of primes are there in this set. So we expect that inside the square root, instead of having just n over log n, we should have n over log n times 1 over pq. This is the expectation, right? However, what we want to bring in is this logarithmic integral, slightly better asymptotic, so that our error terms are sharper. So that's one goal. The other goal is we want to be able to generalize it to primes with Chebotarev conditions, for example. That's the first example that generalizes the prime number theorem, for example. So we want to sort of study it in a slightly different way, so that our methods do not rely that much on the set A, and we sort of know exactly when we are making use of this set A. So that's the goal. Okay. Very recently, Debrun and Tenenbaum have written a paper on asymptotics for these general partitions, and they do this where they have a condition on the Dirichlet series. By Dirichlet series, I just mean Dirichlet series corresponding to set A. I just mean this m to the power s, and m belongs to your set A. And of course, you assume that real s is larger than 1. S is a complex number here. So they have a condition on this, that this function, this is a complex function now. They have the condition that this has a meromorphic continuation to the left of the origin. However, when you are talking about prime, this condition is not satisfied. So we can't really make use of their theorem. So we really have to get our hands dirty and do the work, all the calculation here. So I had mentioned that the logarithmic integral before so this is integral of 1 over log t from 2 to x. The point over here is that you can, just by integration by parts, so once you keep using integration by parts, you can write this as a series, and you can truncate the series at whatever point you want. So you can take m to be 100 if you want. If you want your error term to be much smaller, then you can take m to be million, for example. So the whole point is that you can truncate it wherever you want, at whatever stage. And in that case, the error term will be x over this log x in the log x to the power m plus 1 in the denominator. So any power of log that you want to save, you can do that by putting this in by truncating it at the right point. So in our case, we do not expect the appearance of logarithmic integral directly, but something which is an analog of logarithmic, that is what we expect. And in this case, we end up getting this xi function. I just defined it. I have never seen it before. So I'm just calling it xi z for zeta. So this L over here will be a non-negative integer. Alpha, which is the upper limit of this integral. In the logarithmic integral, it was x. Now it's alpha. So this alpha in our case will be either equal to 1, or it will be the exceptional 0 of the Dirichlet function. So just in case you are already aware of these terms, but the point is that this is some real number and we will be dealing with only when alpha is equal to 1 or alpha is equal to beta, this number, real zero, exceptional real zero. This zeta is the Riemann zeta function, gamma is the gamma function, and this you have over here. Okay, so these are the variables. And if you integrate by parts once again, you end up getting this formula, and the same property is true, that you can truncate it at whatever stage and you can get the power of log of your choice in the denominator here in the error term. Okay, so big O is always denoting the error term. So this is the main term, and this is similar to this logarithmic integral, except that these constants are different. So these real numbers will rely on zeta and gamma. In fact, we can explicitly compute this these coefficients b sub jl. They are in terms of the derivatives of zeta and gamma. So it's like you apply the product rule and then we end up getting this bjl. Okay, any questions so far? All right. So now I would like to state the result that we have for the log of these partition functions. Recall that our set A is the set consisting of all primes in the arithmetic progression A mod Q. The modulus Q is fixed, and these asymptotics or these error terms are in terms when this little n goes to infinity. So the main term here is 1 over phi q. This is what was expected. We expected that. And we also expected here something of the type n over log n. Yeah, but right now I have not given you n over log n, but something in terms of x, capital X. And this function xi is what I defined earlier. And you know that this does look like x to the power alpha over log x, right? This is alpha. So in our case, this is 1. So it's x, capital X over log. It's not n over log n yet. But once I give you the relation between capital X and n, you will see that, okay, this is n over log n. But I haven't given it yet because I want to focus on this error term. Because once I write it in terms of little n, this becomes really ugly and we do not get this nice error term, which is very similar to the error term in the prime number theorem in arithmetic progression. So that's the reason why I have written it like that. This term over here consists of this exceptional character. So these are the characters. Okay, I'll say a few words about that. So if you are not aware of this Dirichlet characters, I'll say a quick word about that. But the point is that there is some exceptional character. We do not expect that it exists, but we can't prove that it doesn't exist. So unfortunately, if we have it, we have to write it. But this term shouldn't really appear. We don't expect it to be there. And this this beta is the Landau-Siegel zero, also known as the exceptional zero for the Dirichlet character. So if I don't write this term, for example, then you don't see any appearance of Dirichlet functions, right? You just see this x over here, this z integral, and this error term. Okay, so now, because I have sort of already told you that the Dirichlet functions appear, the error term should be smaller if you assume the generalized Riemann hypothesis. That's what one would expect generally. But if you just write the theorem here in terms of x over log x, then we don't get it. So that's why we want to write this in terms of this integral z, so that we see the effect of GRH for Dirichlet function. And if we assume that, then of course this will not appear, this term, because this is a real zero of the critical line, and we don't expect that. So GRH gives us this error term to be much smaller. So this is square root of x log x type. And here without VRH, this was much larger term. It was x log q. So we see that this zero free region makes a huge difference. Now the next question is, how about vice versa? Suppose you could prove this result or with some better error term, or let's say just this error term, using some other technology, other technique, not using circle method, which was originated by Hardy and Ramanujan. Suppose you can do it using some other way. Then can you get some result towards the generalized Riemann hypothesis, for example? Will it say something about the zero free region for the Dirichlet? And the next result deals exactly with that. So because the Riemann hypothesis in the previous case made difference only on the error term. So let's write the error term, or let's denote the error term by R sub an, and this will be then by definition the term on the left hand side minus the error term over here. So there should be a bracket over here. And so this is the error term. This result here, this is written in terms of inf and sup, and then it says that this inf is same as this sup. But instead of reading it that way, what you can think of it as is that you have a zero free region for this function, right? So suppose there are no zeros in this area, then the best region or best vertical line that you could get over here is exactly related to this power that you have in the error term. So this mu n to the power mu over 2 is exactly related to this mu over here. And the best zero free region that you could get will give you the best error term, is all that we are saying over here. So because the best zero free region is actually given by the generalized Riemann hypothesis, and this condition is therefore, as a corollary, gives us that the error term will be of this order n to the power 1/4 plus epsilon. So getting an improvement in the error term using any other technique would lead you to getting a better zero free region for the Dirichlet characters. That's the main point that we are making over here. All right. Any question about the statement of the theorem as of now? Okay. So I want to state one more result here. All this while we were talking about the log of P sub n, right? But it's indeed needed for us to obtain the formula for P sub n directly, not just log. And and that is to make sure that our error terms are actually smaller than the main terms. So that's why I just written this formula. You don't really have to look at it if you don't want to. But the main point over here is that you have these exponential part coming here. So the partitions here are also growing like exponential function. And now this formula has not just x. Remember that I haven't really told you what the relation between little n and x is as of now. And moreover, I have brought another auxiliary function theta of 1 over x. Okay. So, but these are the only two auxiliary functions I'm talking about. So you have capital X and you have higher order derivatives of theta. So this is the MRH derivative. But in the error term, again, you only have little n and capital X and theta. Okay. So if I give you the formula for capital X and these higher order derivatives, asymptotic formula, then I have given you all the information in terms of n, right? Remember that the primes are quite mysterious. We even to count the primes up to x, we have this logarithmic integral. We can't really count it in a very nice way with a nice error term. So we sort of have to unfortunately rely on these auxiliary functions. And for the number of partitions, it becomes even harder, and we end up using more auxiliary functions. Now here is the relation between n and x and theta. So n is theta prime 1 over x, and here is the asymptotic formula for the derivatives of theta. So in particular, when I set j equal to 1, I have this formula. Therefore, I will get n equal to that, right? So for j equal to 1, I have this formula. So j equal to 1, that's just x, and this will give me 1 over log x, and this is little n. Okay. So from here, you will get exactly what you wanted. So okay, in the log p sub a n formula, now you have that this is asymptotic to some constant which depends on, let's say, some set consisting of prime numbers in arithmetic progression, square root of n over log n times 1 over phi q. And why is that? Because I get 1x from here and I get 1x from here. So I get x square. And that's why I end up getting square root of n log n. That's what we wanted. So you can only see this cute formula on the right once you have dealt with this thing on the left. So, but here the point was just to focus on the error term and sort of make the error term look slightly nicer, because we want to make use of the fact that if suppose Riemann hypothesis is proven, then what error term you would get for the number of partitions, and this is what you would get. Okay. Lastly, I mentioned something about the monotonicity of Bateman and Erdős. They say that, okay, this function will be, using their result, we can show that our function will be monotonic and it will be going to infinity, but we don't know how fast it will go to infinity. But using our proof, we can actually show that it is also exponential. Even the difference is exponential. So the difference is also going to infinity exponentially fast, because this is true because of p sub a n being of this type here, and square root of n log n in the denominator doesn't play that much of a role. Okay, so now we have this monotonicity, but the whole thing, all these results are actually except the zero free region part, they sort of follow from this theorem. So this is the main theorem to say, and then this requires all of this work, but the other one could be sort of proved using this long formula for, and the expansion for all these derivatives over here of theta. All right. So before I say anything about the proof or how we go about doing this, let's go back to the special case. Partition. So we were talking about partition into primes in arithmetic progression, but if you just set a, q, and j equal to 1, a and q equal to 1, you would get partition into primes. And we already had a result by Vaughan on this. So you want to compare our result to this. So Vaughan had this formula. Of course, he also uses the same auxiliary function, and we expect this to be exactly the same because this is our main term. So this matches with our result. However, the error term that he gets is n to the power 1 over 5. We improve this error term to be square root of log n over n. And this term is actually sharp. This error term is actually sharp because square root of log n over n is not just the error term. If you set j equal to 2, for example, or if you write down the expansion of capital X in terms of n, you end up getting this as the secondary term. So this will actually appear. And then the error term will be log n over n and so on. So of course, square root of that. So this is sharp. If you write it differently, just in terms of x over log x, Vaughan's result gives you zeta 2 over 3 x over log x as the main term. We have this z integral, like the logarithmic integral that you have for prime. And his error term is then of the order x over log square x. However, our error term is of the type x times exponential of this. So this is much smaller than x over log square x. So this is how it compares. So the only difference that you would see here is either wherever he's writing x over log x, we replace that by logarithmic integral, in our case, this z integral, and then we take care of the error term in a more detailed way and make sure that our error terms are not big to destroy our main term. Okay, so that was the example. Now, just a slide for a crash course on Dirichlet functions. So for real s, so s will always denote a complex number. For real s larger than 1, you have this function defined ls chi defined as chi n over n to the power s. Chi is a character over here. So if you want to think of it as a character, group character in the usual way, then this is a character on z mod z multiplicative group. But you can extend it to all the integers whenever your GCD with, for example, in this case, q is larger than 1. And I just spotted a typo. Sorry, this should be chi p. Yeah, because you have to have chi appearing in the second part as well. Okay, and the point is that all the zeros of this function do lie in this critical strip. So they are between 0 and 1 here. So with the real part is between 0 and 1. And the generalized Riemann hypothesis says that all the zeros, in fact, are on this blue line. And this zero beta is the exceptional zero that I've been talking about all this while. We don't know if it exists. We do not expect it to be there, but we can't disprove that. So this is the real zero that we have to deal with. This function will have a pole only when the character is trivial. Otherwise, this one is not an issue. And this region, these red lines that you see over here, this is the non-zero free region. We know that there are no zeros over here for this function. No zeros over here. So they are only like within these parabola types. Okay. And this region is actually of the type 1 minus 1 over c over log t. That's why you were seeing this exponent, the error term of this type. So if you've seen this before, you would recognize that the error term actually already have the information about the zero free region. All right, so this is what we'll be using. And because I mentioned that our, or in the title also, we have the Chebotarev primes. For the Chebotarev primes, we will be using Hecke-L functions, and similar zero free region is true for those L functions also. And they also have this critical strip and so on. So we'll be using that that information about the Hecke-L functions later for those primes. But it's the whole idea is already captured by these Dirichlet functions, or the number of primes in number of partitions into primes in arithmetic progressions. And that's why we want to keep this simpler here on the slide. Okay. So now let me say a few words about the proof. So step 1 is to start with generating function. And this is easy to see that if you want to write n as elements from the set, sum of elements from the set A, then you write this as product P A mod Q 1 minus z to the power p. So now when you write this as a series, then you will be adding all these p's, and it will count how many times you are adding p to get this power of z. So this you can see just by expanding it, writing this as a power series. Okay. Throughout this proof now, I'll be using this notation rho, which is e to the power minus 1 over x. So it's between 0 and e to the power. So x is some large number. Let me say that right away. So rho is going to be really small. X will go to infinity, so rho will go to 0. Also, e of x will be just exponential of 2 pi ix. This is the notation that we just used to make it brief. So this now, quotient integral formula from complex analysis tells us that if you want the coefficient of a series over here, then we can write it as some integral, right, along a circle. So in this case, we write this along this circle, or I can write it as e to the power 2 pi with this notation in mind. This is e to the power minus 2 pi I n alpha, and alpha goes from minus 1/2 to plus 1/2. Okay, so I have chosen this for my convenience, this interval for my convenience. If you've seen this picture before for the eta function, this picture on wiki, when you look for eta function, then it shows you the modulus of the function on the unit disk. But the point is that sort of this picture captures the why it's called circle method and so on. And why do we have these major arcs and minor arcs, why they are called major arcs and minor arcs and so on. So the point is that you see that along this circle, unit circle over here, there are places where you see this blue and then big patch of red and then little blue and so on. So there are these arcs over there. And this is where you see, this is where the function takes a large value. So there are peaks for this function at these points. So now the contribution for this integral, of course, you expect that to be coming from these arcs where this function has peak. And this is called major arc, where the contribution is large, but where the contribution of this modulus of the function is small, then you call it minor arc. In our case, we will have only one major arc, and that will be around the origin. So in the sense of this picture, this is where we will have our main contribution from. This is the point 1. So this is where we will have contribution from. So now you'd have to decide the length of your major arc. Like you want to integrate from minus 1 to 1/2 to 1/2, right? So where would you expect the most contribution to come from? Well, it's one can realize that it's going to come from an arc around the origin. Okay, so this is interval around the origin. So this is it. But the length of the interval right now, I have written it as minus x to the power minus 4 over 3. It's really small, 1 over x to the power 4 over 3, and x goes to infinity. However, I have already done my math, and I'm just giving you the answer for here. So otherwise, you would just call it something, some length something, and then you optimize this length, and then you decide later what length it should be for the major arc, so that the contribution that you get from this extra red part, for example, over here, then that's not too much. That's not bigger than the contribution that you get from this part, right? You want to make sure that you have a main term, and the error term is smaller than that. Okay, so as of now, I have only applied the quotient integral formula, but when you are doing complex analysis, there are many ways of computing this integral. Well, not exactly computing, but estimating the integrals. And that's all we care about. We can't really count well. So we are happy with the estimate. So to start with, we first compute these estimates. So the major arc, the integral around this interval, blue interval here. And the idea over here is that the integrand is this, right? You already have an exponential something, but you also have this c. If you could write this as exponential of something, the whole integral is exponential of something, then you could apply Taylor's theorem, right? Because we know the Taylor series expansion for the exponential function. That's all we do. So we first write this integrand as exponential of something, and then we write this Taylor series extension for the exponential function. Okay, so writing it exactly, I have written this way. But for the Taylor series extension for the exponential function, we truncate it. Instead of writing it up to infinity, here I take it only up to g. Okay, and then the rest part goes into error term. Right now, you can't really see that this is actually an error term because you don't see that this contribution or the asymptotics for this will be smaller than what you would have here. But trust me, because I have already I'm sort of giving you the answer now, but this will end up being the error term. Now I have written all these lambda k's, lambda L k function, which do not involve alpha because I have to integrate with respect to alpha. So I'm just like whatever doesn't involve alpha, I'm just sort of putting that together so that it doesn't make a mess. So I have alpha over here and I have to integrate with respect to alpha. I have alpha here and then I have alpha here, right? So now we can easily integrate this. Okay. So just integrate that and we end up getting this formula. Okay, so this integral along that blue interval is given by this formula. Well, what is, so this lambda L sub k does involve my theta functions, and I also have the higher derivatives of theta over here, but they are more over here. So this is one and so on. So if I can find asymptotics or if I can estimate these functions, auxiliary functions, then I will have a main term. So now the next goal is to find the asymptotic for this derivatives, higher derivatives of theta. Okay. So once I do that, then I will have the nice formula, at least for this integral. I still haven't touched the minor arc or the red integral yet. I'm still talking about the subinterval around the origin. Okay, so by definition, the jth derivatives of this function is given by this. My p is the only part where it appears where this is related to the set A, where my parts are from, right? So my partition, my parts are from P congruent to A mod Q, and then there is this P to the power G. That's the only thing. This will appear whatever A you would take. This term would appear whatever A you take. Okay, so now we as you saw earlier, we could sort of happily, in some sense, deal with the integral, but we can't really count. So we want to move from summation to integration, and using Mellin transformation and inverse Mellin transformation, you can switch between the two. So now we write this in terms of the integral. Okay, so with this sum here over k and this sum over p, the sum over p remains over here, but the sum over k will give you zeta, Riemann zeta function. This is k to the power j minus 1 from here, and there will be 1 k to the power minus s coming from the Mellin transformation. So once you have applied this, you end up getting this term. Okay. Now again, you see carefully that this part does not involve anything that your set A was related to. Your set A consists of primes in arithmetic progression. And this is the sum that you have. So you have very nicely separated this part which involves A, capital A, the set A. Okay. So if these were not the primes, this would be, if it was any natural number, it would be Riemann zeta function, much easier to deal with. However, this is sum over primes. So this turns out to be similar to log zeta rather than zeta. But now we also have this congruence condition. So P is congruent to A mod Q. So now you have switched from zeta to the Dirichlet characters log L. Okay. So you will have this log L factor. So you are also using the orthogonality of characters over here to switch or to put this condition of P congruent to A mod Q. So here there is no A mod Q that you see over here, but I have put that condition by summing this over the characters. So this is using the orthogonality. And then now you have this integral from minus on this vertical line. So eta minus I infinity to eta plus I infinity. And then there's this error term that I have written because my sum here, my sum here was over P. So it was P to the power j minus. So it was not exactly log L. There is some error term, and that's the error term that you would get here. Okay, and this is the line along which you are integrating, this line on the right hand side, but you can't really integrate it and get a good estimate. So you change the contour and sort of get the main term by including a pole of your integrand in it. Okay, so now we will change this contour. Instead of going straight up, we follow this blue line, and then we recall that this was the zero free region. So we can't really enter this part. So this is forbidden forest, you can call it. So you can't go. This is not allowed. So you have to stay only on this side. Okay. So instead of now going up straight, you take a left turn, and you already know that one is a pole. So again, you can't really include it, but you go around it. Okay. So this is, and then this is the contributor. Then you go back to this blue line. So now I will apply residue theorem or Quotient or the Cauchy's theorem, you could call it. But here you see that there is a logarithmic singularity at this point, 1 over here. So this is where this part that you see over here. So let me use this pink color over here. This part, this will give you the main term and the estimates for the integral along these green lines, blue lines, all will go into the error term. That's my claim over here. So then you apply the upper bounds for the log Dirichlet zeta function, gamma function, and you estimates or you get this error term, and it turns out to be indeed smaller than this part over here, and you can exactly compute this. So you get rid of this integral now by actual terms, actual function. So this is what you would get, and that was our claim. So now what we have done so far. We have the integral of the function. We wanted to compute the integral from -1/2 to half. So now we have computed the integral around the origin 0 in the blue interval. In that, we had some functions, auxiliary functions, theta j, higher order derivatives of theta. We have obtained an asymptotic formula for these in terms of this. Now what we are left with is only the integral along or away from the 0 region, right? So now we need to compute this part, integral along this. So this we have already done, or we just did that. Okay. So now going back to this part, recall that this was the integral for the blue part. So this is blue. Now I have just written everything together, and we already know these asymptotics for this. The minor arcs is now this red part over here. It doesn't matter whether you're on the left of the origin or to the right of the origin, you will end up getting the same estimates. So recall that our phi was the generating function for the partitions. we find bounds, upper bounds for this function depending on this range of alpha. So we know that alpha is in this subinterval. It's larger than x over, let me just write it. This part was x to the power minus 4 over 3. So this is larger than x, this quantity, and it's smaller than 1/2. Well, okay, we have two estimates. It's not uniform in this interval, but when it's of this type, when mod alpha is less than 1 over 2x, then this is one quantity. The point to note here is that there is an alpha here. It's alpha square, because ultimately we will have to integrate with respect to alpha. So we still have an alpha coming from here. But when alpha is closer to 1/2 here, but larger than 1 over 2x, so it's much larger than this boundary here, then you do not get any alpha here. So then you don't really need to worry too much about the integration, because then it's like just along this small interval and you are done. So this part is good. So this is not creating an issue. But when you integrate this, again, you have to keep, like when you integrate it, you have to make sure that when you truncate it, you end up getting something that you want. However, the proof of this part is the one that involves combinatorics, and you have to be really careful, because even though later it doesn't create a problem, just to get this bound, you have to exactly, or you have to get sharp bound. Okay, not sharp, but you have to get nicer bounds, otherwise you won't really get the theorem at the end. So this requires work right now. This will require work much later. Okay, so now let me just point out one thing, that in order to get that quantity, that upper bound, the main idea is that once you use the right definition, or exactly the definition of this function phi, you relate it to relate the sign function to the nearest integer distance function. So in the absolute value, earlier you just had the absolute value. Now you have this integer distance, nearest integer distance. And once again, this is the only part where you have used the fact that your parts were coming from the set A, which consists of primes in arithmetic progression. Okay, so this is again this part. So now, if I want to generalize my theorem to some other set, if I could compute this part for m in A and m bounded by x, and then this function alpha times m, then I will be able to get this identity. So I will be able to ultimately compute this integral. However, this is again, I mean, this depends on what numbers you can count. We can't really count every numbers of this form, but in this case, it just primes in arithmetic progression, and the prime number theorem tells us what it is. Okay, so okay, I have some time, so let me just say a few words about this. So we will be applying Dirichlet approximation theorem, and in order to compute this. So now the goal is to compute this, right? Summation, sum over p. Now p is always in this arithmetic congruence, arithmetic progression. So now, once you have the Dirichlet approximation theorem, you can say that, okay, alpha is close to some rational number, and let's call this rational number as L over K, for example. Okay, and now I have L over, so I need to now find this distance, nearest integer distance of alpha L over K, right? Okay, so now, because of this negative sign in the exponential, because I need an less than equality, that means I need to find a larger than or lower bound for this quantity. So we know that, okay, this number should be larger than 1 over k, right? Because this is just residue, except when k divides L or k divides alpha, but k and L are co-prime to each other. Oh, I should, sorry, this is P. my alpha is L over K. So I end up, and my K will not really divide P unless K itself is a prime number. So there aren't many such primes because you have only one K, which is fixed. So there aren't many primes which will be divisible by K. So now you want to find, so you want to replace by this 1 over K quantity over here. And then once you have done that, let me say this very quickly. Now this will be 1 over K square P congruent to A mod Q and P less than X. However, now you also need how many distinct conjugacy classes are there in the P. So this times distinct conjugacy classes in the set. What did you have? I had P times L in the set. P less than X. X is L is fixed in this case, and P is again in the arithmetic progression A mod Q. So this condition will always be there. So how many distinct conjugacy classes are there in this set? So that's what you need to write. Of course, once again, we can't really count that. So we find an upper bound for this. Lower bound for this. So we have at least let me just write this as, so we write find, so okay, and then larger than equal to some quantity, let's call it some star, and then now this is easy to compute. Now you can compute this sum over here. So in the beginning you had this generating function ratio over here. You converted that to this nearest integer function, and then you counted the number of distinct conjugacy classes that you have. You find a lower bound for that, and then you sum over these primes. And the sum over primes is done by prime number theorem. So that's exactly where you were using the fact that was the set from which your parts were coming. So now ultimately this part again does involve your primes. So as long as you can deal with this set and this sum, you can get the answer. And in our case, we can do this for primes. Okay. So once you have this, then you are able to compute this integral over here, which was, so this is 0, this is not the one, so minus 1/2 and 1/2. So now you are able to compute the integral over here, the green part, and that's equal to this. So now you have computed the integral which is away from the 0. You had already done it for the point for the interval which was around the origin. So you have done all this integrals, and once you put this all together, you get the answer. The formula that I will not write again, but you have the formula that was claimed. So this is what you would get. This is the end of the proof. Lastly, I want to make a remark about the Chebotarev primes, how they are different, or what needs to change in the proof. So for this setup, you have a Galois extension L mod K, finite Galois extension, and then you have a conjugacy class C in the Galois group. You will have this Artin symbol for the primes in K, which are unramified in L. What we want to partition now is we want to partition N into norms of these ideals, and because there could be more than one ideal of the same norm, then these numbers could be same. So that's why, because we want to keep track of these, so these will be colored partitions. So, and the number of colors will change with the prime here. So this is not like we can decide in advance that we have 5 colors. That's not the case. So this will depend on the prime. With this setting, if you take this special case when L, K, and everything is just the base field Q, then your set A will be just the set of prime, which we have already talked about. Now, the recently talked about case was primes in arithmetic progression. And if you take this field extension, K is still the base field Q, and L is this qth root of unity, Q adjoined with qth root of unity. In that case, the Galois group will be the multiplicative group over Q, Z mod Q. And the conjugacy class will be just a fixed residue class. And that gives you the primes. In that case, we are talking about the primes in arithmetic progression, A mod Q. Whenever you have this base field K equal to Q, you will have only one color. This is because we have only one ideal of that norm. So once you change your K, the base field K, then you might have more colors, and then the color partitions get into the picture. But if you are happy, or if you are just interested in the base field in Q, then this is just a simple partition, not a color partition. Okay, so this is the special case. And for the prime number theorem, so all this while we have been referring to the prime number theorem, right? So for this also, there should be some version of prime number theorem that we can refer to. And there indeed is. It's called Chebotarev density theorem. And its effective version was given by Lagarius Orlisco in 1980. And they counted the number of prime ideals with norm bounded by X, so that the Artin symbol is given by this conjugacy class. And they have this main term, mod C or mod G, times the logarithmic integral. So logarithmic integral we expect, right? We had it for the number of primes, we had it for the primes in arithmetic progression. The main point is what the coefficient of this is. In the special case when we were talking about primes in arithmetic progression, this was 1 over phi q, because the total number of elements in the Galois group, Z mod QZ under multiplication, has exactly phi q elements. And the conjugacy class had exactly one element. So that's why you had 1 over phi q. But now Galois group could be different. The number of elements in the conjugacy class could be different, and so on. So you get this error term. Here NL is the degree, and DL is the discriminant of the extension. We saw this appearance of exceptional zero in our case as well. They have put this in the error term. And again, we do not expect it to be there, but it's just there. And the fact that it is smaller than 1 gives us that this is the main term, because this is X, and that's X to the power beta. Okay, so which is smaller than 1. In our case, the version for the number of prime coming from this set A over here, the log of that will be asymptotic to mod C over G, as we expected. Instead of the logarithmic integral, we would have this xi integral, and this will be sum over 2 of them. L is 0 and 1. And this is again the corresponding term for the exceptional character. And this is the error term that we would get. So this is, again, this one I did not write in terms of little n, even though the left-hand side is a function of little n, the right-hand side is a function of capital X. The relationship between X and little n is the same as described before. And if we write this in terms of n, then we won't get such a pretty formula. So, and we won't be able to see the relationship with the corresponding prime number theorem. So that's why we are again writing this always in terms of X, but also giving an asymptotic formula for relating little n and X. So yeah, with that, I'll end. Any questions are welcome.
All right, thank you very much. Are there any questions? That does not seem to be the case. So yeah, thanks again, and I will stop the recording.
Yes, thank you again.